So, let me just quickly first go through a very interesting application, right, of this notion of SMT, which is bounded model checking. Okay. So, this is kind of to motivate, right. I mean, so far all our discussion, right, has been focused on just building the various blocks, right, your propositional logic, first order logic, SMT, that we are going to use, right, but we haven't really done any verification as such, right, we haven't even looked at programs. So, let us look at a very simple example, right, of how we can use SMT in order to perform what's called bounded model checking. Right? So, what is bounded model checking in general, right? So, in general, right, given a transition system, a property and a bound K, bounded model checking determines whether a state satisfying the property is reachable within K steps. Okay. So, again, right, we will see bounded model checking in detail later on in the course, right, but to just give you a very sort of brief idea, right, given a transition system, right, so transition system is just it's a set of states and a transition among them, right. So, if you have some property and a bound K, so you want to check whether or not starting from some initial state, right, if you were to perform K steps in the transition system, whether you reach a state where this particular property is violated or not, right. So, whether a state satisfying the property is reachable within K steps, okay, that is what is called bounded model checking. Now, in the context of program verification, right, or programs, right, this bounded model checking, right, is useful for finding bugs in programs, right. So, in this context also called symbolic execution, right, and BMC is actually the basis, right, of a number of highly successful automated bug finding mechanisms, right, such as concolic testing, white box fuzzing and so on, right. So, let us see how BMC looks like in bug finding. So, in order to motivate this, right, I am going to use a real world example, right, which is from this Microsoft Zune. Okay. So, what is Microsoft Zune? So, this was a portable media player that was introduced by Microsoft in 2008, but discontinued it in 2011. Right? So, that is why you do not see it around now. So, this particular product had a very interesting sort of buggy scenario, right. So, what happened was on December 31st, 2008, which was the same year it was released, all Zune devices suddenly went silent. And then on the very next day they started working again, right. So, in fact, the reason why this happened was there is a very subtle bug, right, and what we are going to see is where this bug is, and we are going to then try to find this bug automatically using BMC, right. So, here is the Microsoft Zune bug, right. So, this is a very simple piece of code, right, which is taken from the code, right, that was present inside Microsoft Zune, and this code, what it does is it converts days to years, right. So, it is a function, right, which days to year, which takes as input the number of days, right, and then it computes how many years have passed. Okay. So, the way it does it is quite simple, right. So, it starts off with 2008, right, which is the year in which Zune was introduced. So, if the number of days that have passed are greater than 365, right, then essentially you want to say that 1 year has passed, right. However, there is this leap year thing that you need to take care of, right. So, if the current year is a leap year, right, then the number of days must have crossed 366, only then 1 year has passed, right. So, if the number of days are greater than 366, then you will increment this year by 1, right. In each case, right, you will decrement this days, right. So, in this case by 366 and in this case by 365, and then you will continue this loop, okay. And finally, you will get the current year, right, based on the number of days that have passed. Now, it is this piece of code that would get stuck, right, on when the exact day is December 31st, 2008, right, and why is that the case, right. So, if you look at this code, very closely, right, so you will see that first of all 2008, right, this is a leap year, okay. On December 31st, 2008, how many days would have passed? So, the number of days that would have passed would be exactly 366, right. So, you would have passed exactly 366 days, because there are 366 days, right, in a leap year, right. So, which means that you would have called this function with days equal to 366, right, and in fact, if days is equal to 366, it is going to go inside this loop, right. So, it is going to go here because 2008 is a leap year, right, but this particular condition is not satisfied, right. So, days is not greater than 366, days is in fact 366. So, therefore, this loop, so it's not going to enter this particular conditional, right. So, now it's just going to return back, right, to this loop, return back to the start, right, the next iteration, without any change in the number of days, right. So, in fact, this particular loop, right, is never actually going to terminate, right. So at days equal to 366, this while loop terminates or rather iterates infinitely, right, and that's why the Zune devices actually got stuck. Now as a homework, right, you can try to kind of repair this program, right, and solve this issue, right, so that this particular problem goes away, but that's not what we are going to focus on now, right. So let's try to focus on how we can automatically find bugs like this using SMT, right. So remember that in order to find this bug, right, you have to do this very careful reasoning, right. Okay, what should be the value of days, what should be the value of year that I have to pass, right, so that this particular code gets stuck. Let's see how we can do this automatically using SMT. So how to specify the correct execution, right. So what is it that we want, right. So we want to say that this code should never get stuck. That's a correct execution for us. So remember at the very beginning, right, of this particular course, right, we had talked about specification, right. What should be your specification? So the specification can be very complex, it can also be very simple. So in this case my specification is very simple, right, that this code should not get stuck, which means that this loop, right, should not run indefinitely. It should definitely terminate. That's what I want to say. Okay. So the way I can say this is by adding this assertion, right. So I have made one change in this code, right. I have first introduced this variable old days, right, which is assigned to this days variable at the beginning of the iteration, right, and then at the end of the iteration, right. So at the beginning of iteration I log essentially what is the value of days, and then at the end of this iteration, right, I check that days should be less than old days, right. So old days was the value of days at the beginning of the iteration. At the end of the iteration, the value of days should be less than old days. Okay. Now you can convince yourself, right, that if this assertion holds, right, if it is true in fact that this number of days are always decreasing, right, then this loop will definitely terminate, right, because every time that you execute an iteration of the loop, you are going to decrement, right, you are going to decrease the number of days, right, this days variable is going to decrease, and eventually it will, this particular conditional will not get satisfied, right, because days will become less than 365, right, because days is always decreasing, right. So even if you started with a very big value of days, right, then after every iteration, right, you are going to keep on steadily decreasing the value of days. Eventually, right, this condition is going to fail. Okay. So therefore if this assertion is true, then my loop is definitely going to terminate, right. So this, which means that the program will definitely not get stuck. Okay. Now what we are interested in is violation of this particular assertion, right. So we want to ask, okay, is there a value of days that I can start with, right, is there an year that I can start with, such that this assertion does not hold, right. So this assertion is violated. So we are looking for violations of this assertion. Okay. Okay. So now let's try to step by step convert, right, this particular program into an SMT formula, right. The first step is to unroll the loops in the formula, right. So in this particular program we had loops, right, which is this while loop. First we are going to unroll the loops, and this is where this BMC, right, this bounded, the term bounded comes into play, right. So you are essentially only looking for a bounded execution of the program. In this case you are just unrolling the loop once, so we are only interested in one iteration of this particular loop, right. So let's see what change we have made, right. So we have converted, so if you look at this code, right, this while loop has been converted into an if block, right. So we are saying if days is greater than 365, then you enter the iteration. So this is the first iteration, right, and then we are not going to revisit this particular while block again, right, which means I have converted the while to if, right. So there is, so you will only at max visit one iteration, right, and again we have the same assertion, right. So we are logging the value of days in this old days variable, and then we are asking whether or not days is less than old days. In addition, we are also adding this assertion, right, that days is less than or equal to 365. So in fact if days was greater than 365, then I would have actually continued, right, in the next iteration. So I am saying that I am only interested in one iteration, right. I am only interested in executions where this loop is only going to contain at most one iteration. Okay. So we have unrolled the first iteration of the loop, right, by converting from while to if, right. So if this assertion is violated, right, if the first assertion is violated, that means that we have found a valid counter example, right. So the assertion violation means that the value of days is in fact not less than the value of old days, right, which means that this loop, right, may not terminate, right, because in an iteration, right, you are not changing, you are not decreasing the value of days at all, right. So if the first assertion is violated, then we have a valid counter example. What about the second assertion, right? So we have added one more assertion. So if this assertion is violated, then that means two things, right. see, the very fact that you reach this assertion means that this assertion has passed, right. So which means there is no counter example involving only one iteration. So using just one iteration of this particular loop, right, I cannot violate this assertion, the first assertion, that days is less than old days, right. But since the second assertion is being violated, it means that there are executions where the value of days will in fact not be less than or equal to 365, right. It will be actually be greater than 365 when you reach this particular program point, which means that you may continue, right. So there may be executions with multiple iterations, right, and in fact there may also be counter examples, right, involving more than one iteration, right. So in this case, this is why it's only bug finding, right. So it either finds a bug, right. So if the first assertion is violated, then we have found a bug. Otherwise, if the second assertion is violated, then we don't know, right, whether a bug exists or not, right. All we can say is there is no bug involving just one iteration, but there may be bugs involving multiple iterations. Okay. So if none of the assertions are violated, then no counter example exists. Okay, so now there is a very simple sort of conversion, right, that we will use in order to convert this particular program to an SMT formula, right. So as the first step, we will convert this program into its SSA form. So SSA is static single assignment, right, which means that we replace every assignment of a variable, every assignment to a variable by a new variable instance, and we replace users to appropriate variable instances, right. So from the previous program, right, on the previous slide, the only difference here is I have added these versions of variables, right. So we have essentially new instances of variables, right. So every time that a variable is assigned a value, it is assigned to a new variable instance, right, a new instance of that particular variable. So here, if you look at if you focus on the variable year, right, so I have year 0 here, which is assigned 2008, right. Here is another assignment, right, which is year 1. So here I am using another instance of the year variable, right, which is year 1 equal to year 0 plus 1. Similarly, here there is another assignment where I am using year 3 equal to year 0 plus 1, and so on, right. And every use of a variable is also replaced by its appropriate instance, right. So for example, here there was only year, right. So earlier you had year equal to year plus 1, now you have year 1 equal to year 0 plus 1, right. Similarly, here I have year 3 equal to year 0 plus 1, right. Similarly, you have days 0 here, right, old days, and so on. Okay. So again, there is this is a very well known procedure, right, which comes from the domain of compiler design, right, which says how to convert a program into its SSA form. Okay. So once you have a program in its SSA form, you can just directly convert this into a sequence of program statements, right. So what we have done is we essentially took this original program, right, which contained this if, right, which contained actually nested if then else's, and we have just replaced it as a sequence of statements, right. And what we have done is we have introduced some Boolean variables here, right. So this G0, G1 and G2, these are the 3 Boolean variables that we have introduced, which correspond to the 3 conditionals, right. So there are 3 conditionals here. So this is G1, this is G0 rather, this is G1 and this is G2, right. And what we are saying is that the value of these variables, right. So for example, days 1, year 1 and so on, right. This value is assigned, it's dependent on whether or not these conditionals are true or false, right. So in fact, if for example, right, if you see this particular assignment, right, so it says days 2, right. So it's using this particular notation phi, right. What this means is that if G1 and G2 are true, then days 2 is assigned as days 1, otherwise it is assigned as days 0, right. So this is how you can read it. So this is like if, right, then and else, right. So what that means is at the end of we are looking at this particular days 1 assignment, right, and after you execute this whole block, right, what will be the value of the days variable, right. So we are saying that if both G1 and G2 are true, right, then the value of days 2 is going to be days 1, right, otherwise it's going to be days 0, right. So this days 1 assignment only happens if both G1 and G2 are true, right. Similarly, year 2 is equal to the same thing, right. So phi of G1 and G2 year 1 comma year 0, right. So if G1 and G2 is true, then year 2 is assigned year 1, otherwise it's assigned year 0, right. And the other part, right, which is the else part, right, is being used here, right. So it's saying that if G1 is true, right, then days 4 is assigned as days 2, otherwise it's assigned as days 3, right. So again, it's just directly encoding, right, the effect of these 3 conditionals, right, which is G0, G1 and G2 on the value of these variables, right, and what is the value of the particular variable depending on what condition is executed, right. So again, this particular conversion, right, can be done automatically, right. So there are algorithms, right, which come from the domain of compiler design, which you can use to convert to this SSA form, right, to this static single assignment form. So once you have this static single assignment form, right, and all of this so far is known, right, is coming from the theory of compiler design, you can now directly convert this into a formula, right. So in fact, the way to convert this into a formula is just directly replace, right, the semicolons with ands, right, with conjunctions, okay, and that's all, right. So I say year 0 equal to 2008, right, G0 is day 0 greater than 365, old day 0 is equal to D0, day 0, and G1 is leap year 0, and so on, right. This size, right, I have replaced it with this ITs, right, IT is just if then else, right. So you can think of this like G1 and G2, right, implies that days 2 equal to days 1, right, and not of G1 and G2 implies that days 2 equal to days 0, right. So that's all it means. So all of these, right, so you can see that this entire thing now, right, is a formula, right. So in fact it's a formula in first order logic, right. And one other thing that I want to kind of highlight is the assertions, right. So what have we done with the assertions? So remember that we are interested in violations of these assertions, right, because assertion violations correspond to bugs. So in this case, I have just negated the assertions, right. So I have said not of days 4 less than old days 0, right, which means I am interested in negating this assertion, right. So I am interested in value of days 4 which is not less than the value of old days 0, right. In fact, it is greater than or equal to the value of old days 0, right. Similarly, OR of these two, so OR of both of these assertions, right. So now that I have this SMT formula, right, this is a formula in first order logic, right, what are the theories that are being used and what is the question that we should ask, right, whether we should ask satisfiability or validity, right. So let's first answer what are the theories which are used in this formula, right. So now you can see that this particular formula, right, this is using obviously numbers, right. So there is 2008 to 365 and so on, right. It is also using equality, right. So is it the theory of integers, right, or the theory of natural numbers, right. But there is also this particular function, right, this is leap year 0. So is leap year is actually an uninterpreted function, right, because its implementation is not part of this particular formula, right. We do not know how is leap year actually works, right. So it is uninterpreted, right. So that is why this formula, right, is in fact in the theory of integers, right, it is linear integer arithmetic, and in the theory of equality, right. So it is in the combined theory, right. So this is an example of a combined theory. So it is in a combination of the theory of linear integer arithmetic and the theory of equality because of the presence of this particular uninterpreted function, right, which is leap year, right. And in fact, in this combined theory, right, the question that you are asking is this formula satisfiable or not, right. So is it satisfiable? Does there exist a value, right, of all of these variables, right, such that this entire formula becomes satisfiable, right. And in fact, this formula is satisfiable, right. So for day 0 equal to 366 and is leap year 2008 equal to true, this formula is satisfiable, right. And this is what we had also informally deduced, right. So by just looking at the program, right, we had kind of made this formal, we had made this informal reasoning, right, that if you execute this program with the input days equal to 366, right, and is leap year 2008 equal to true, then this particular program is actually going to run indefinitely, right. So it is not going to terminate, right. The while loop is not going to terminate, and by just directly using techniques from compiler design, right, which is static single assignment form, right, and by using decision procedures from combined theories, right. So what we get is an SMT formula which is in a combined theory, right, and then by using decision procedures from the combined theory, right, we can actually just directly answer automatically whether or not this program, right, does it have a bug or not.